before we kick off, just a little bit of health and safety stuff. In the event of a fire or any other emergency, please just follow me calmly out the doors, and we'll go out through the stairwell. And if you're looking for the bathroom, head back out the doors you came in, and look on your way out to the left. There's a bathroom sign on the door to the stairwell. You go right through the stairwell out the other side, and then to your right down the hallway, and you'll soon see more signs, and that's the bathrooms. And today we're going to have industry highlight lightning talk, followed by the keynote, and then we'll have some Q&A, as much as we'll need for that, which is usually tons. And yeah, I missed anything else? Oh, obviously thanking IBM for the amazing refreshments and this amazing venue. So let's give IBM a round of applause for supporting the meetup and giving us free rein to keep doing our community-driven thing. It's amazing and super helpful what they do. And yeah, so first person I'll be working with today is Caleb Moses, and he does data science at dragonfly.co.nz, doing all kinds of exciting and quite meaningful research. So please welcome up Caleb.
We'll see if it works.
We'll do the HDMI cable dance.
Oh, right.
Usually,
here it is. Yeah, sorry about that. Cheers.
Cool. So the camera is all set up for you to be kind of standing over this side, Caleb, when you're ready.
Okay. Yep, that's fine.
We're usually down listening, and we usually have microphones that actually... But today we have half of the AV system malfunctioning, so if we could be pin drop quiet during the presentation for our guests, then we can save them from losing their voices, hopefully, while they do their presentations. So, Caleb, I want you to just click this to your lapel when you can. That's just for the recording.
Okay.
Thank you so much.
Right. Oh. All right. Let me think. I have. What are the odds that I can keep a connection for however long this is going to take?
This is still on. You can turn it off and on again if you like.
Yeah, give it a go.
It does the trick.
I can always... Excuse me.
On.
Let me know if it shows. Nope. Yeah, I can't see you yet. That's okay. I'll hotspot myself.
Okay. Or if you can't see, bring this back up on shot. Ah, the wired hotspot.
Yeah.
That's going to be fine.
Okay. We good? We good. Okay. Let me move this over here. F11? Okay. Cool. Okay, hello everybody. My name is Caleb Moses. I work at a place called Dragonfly Data Science. We're a data science consulting firm based in Wellington. But I'm kind of the lone wolf up here in Auckland. Basically, I grew up here. And I spent a couple of years after doing postgrad maths working for Stats NZ, and then I switched over to Dragonfly. My condition for switching was, in 6 months, let me come back home. So yeah, so that's what I did. So now I'm up here and doing all sorts of fun stuff. So who am I? I'm an Aucklander. Hello. Grew up out west, and I'm Māori, so I'm from Hokianga. Yeah. Ko ngāpuhi nui tonu tōku iwi. What else? I do machine learning at Dragonfly. We kind of do a lot of things. My work has more leaned towards the machine learning side, but like other people are like kind of super crazy good statisticians and all that sort of stuff. I care a lot about AI ethics and data privacy. When I worked at StatsNZ, I used to work on data privacy stuff to do with StatsNZ's central database. They have this database called the IDI where they link up information about individuals across different sectors of government. So they link up your justice records with your education, with your tax records and all that sort of thing. They use it to study, well, all sorts of stuff, crime, health, link up some external data set to something so you can get some sort of longitudinal view and do some cool studies. And I'm also a language nerd. I speak Japanese fluently. My Korean is okay. And I speak some Māori as well. But my Māori is not the best. Okay. Right. So Dragonfly, this is how I like to explain Dragonfly to people because it's not very clear. And when you see the different stuff that we work on, you'll kind of get my point, which is that it's not very easy to say, this is what Dragonfly does, So we're a bunch of environmental scientists. Pretty much everyone other than me is some sort of, fisheries scientist / ecologist / all of those various things. We're all Bayesian, so Bayes by default, basically, at Dragonfly. We do lots of machine learning stuff, and we're also, as people like to say, we're also all about automation. Basically, I can just show you. So this is everyone in Dragonfly. So there's Ed, CEO, Finley, I call him second in command. They co-founded Dragonfly together. There's me, Philip and Richard. Richard's our back-end guy. Philip is, I call him the card-carrying climate scientist. So he goes to the conferences in Washington and listens to all those talks between the Japanese and the EU. Katrin, I forgot to mention her. She's our editor, So whenever we write articles, research articles, she runs through them, and makes sure we got all the references right, and she's much better at picking words than I am, which is quite cool. And then there's Ivan. He's an ecologist, and he's a super R geek. He's very far down the R train. And Laura is she's the newest, but she only arrived a couple months after me, and she's a fisheries scientist who works mostly with Philip. And that's it. That's all of us. So because there's only 8 of us, we like automation because you can't have one of us doing routine work over and over again because then that routine work doesn't make money. So that's kind of the point. Anyway, so that's who we are. So I just want to tell you who we are, some cool stuff that we've done, and then lightning talk complete. So this is one random thing. So basically, I don't know if anyone's heard of Montu. I think they mostly serve international clients. But Montu is a startup-y thing that's based in Wellington that does actuarial modeling. And basically, we did some stuff with them modeling price elasticity. But because we're Bayesian, you set up a proper Bayesian network, make all your assumptions about how the world works, and then you can use it to interpret. You can interpret your model, and in so doing, kind of get extra information out about whatever it is that you're learning. We do stock assessment for lots of things, but one of them is the white-tip shark. We've done stuff on turtles, kakapo, various kinds of seabirds, just basically, population estimation, but for in the context of ecology and modeling environmental pressures and all that sort of thing. So that gives us one of these maps of basically how long your white-tip sharks are depending on where you go. Length being a proxy for age, I assume. I'm not a fishery scientist. So that's another cool thing. I'll refresh this because it tends to bug out. So we're the official scrutineers for the Bird of the Year. This is a funny story. Basically what happened is that 2 years ago, the Bird of the Year competition happened, and then what happened is it got hacked. So some person made some botnet, bunch of email bots that just spammed the network, and then all tried to vote for the same bird. And it happened to be the case that when that happened, one of our guys was actually following the election. He had some code that was just repeatedly scraping the website, counting how many votes are coming in, and then when he saw the spike, he was like, oh, he told Forrest and Bird about it, and then they took it to the media, and then it became this big thing. He was like, oh, people are hacking our Bird of the Year, you know? And this, what you're seeing now is the results for Bird of the Year 2019. Our data scientist, Yvonne Richard, he put this together. He's like now, ever since he got that taste of fame from the hacking incident, he's always following Forrest and Bird now. And yeah, so we have this kind of amusing relationship with them. Yeah, Yellow White Penguin won, by the way. I was Team Kakapo, just saying. We came second 2 years in a row. Another thing that he did, which is quite funny, is he put together this map of the number of votes for Bird of the Year this year. And this one went viral. Does anyone know why? Yeah?
Was it because Russia had like a bunch of votes?
That's correct. Yeah. So if you look at the color map, it's on a log scale, but which means that here in New Zealand it's like 10,000-ish, but like Russia, it looks like it's half, but it's not. Like from Russia, there was only about 300 votes. This one, it made it to the Washington Post. And I won't bother to go through the stuff they add, whatever. But yes, I just thought I'd show you that. So let's see. Is it gonna let me back? Oh, here it is. Here we go. Yeah, so Bird of the Year, Scrutineers, Dragonfly. And this is another project that we did, which is pretty cool. It's called Kokako. And basically, it's the solution to a problem that started somewhere around 3 years ago. Basically, so we've got 21 iwi radio stations. The dots, that's where they are. And the iwi radio stations, basically, they get funded by a government agency called Te Māngai Paho, who fund all of the, well, a lot of the iwi, the Māori media, you know, so like Māori television, all that sort of thing. And basically what happened was that some minister at some point said, okay, I think that the iwi radio stations should produce no less than 10.5 hours of Māori language content every day, right? So they make a rule, you know. But what that means is that now Te Māngai Paho have to measure how much Māori is on the radio, and this becomes a big problem for them because there's 21 stations, and they're broadcasting in real time constantly. And so how the heck do you do that? So Te Māngai Paho, they used to pay people to listen to the radio, and like try and sample it and be like, you know, oh, is that Māori? Is that not Māori? All of that sort of thing. And it was kind of hell, even for the people who were doing it. And basically, Dragonfly worked with them to build a machine learning model to do the work for them. The model that they built, it's like it was originally made for birdsong. So the idea was that you would deploy a grid of microphones in the forest, and then anytime you hear a bird chirping, then you have a machine learning model that identifies the bird and then logs an event. You know, so okay, in this part of the forest, I heard a kokako, or I heard a kiriru, or that sort of thing. But what's also cool is that I don't have to just tell you about it; I can show you. So this is the kokako interface. So let's go Radio Watia, and this is all of the Māori language content that's on the radio. So the red is Te Reo, blue is English, yellow, hard to see yellow, but if we do this, if we do that, so there's some yellow bits there and there. That's kapahaka music, labeled by a fingerprinting system, and the Māori music is fingerprinted as well, right? So you can kind of see, if I go here and then here, let's go. Let's find an interesting spot. You look interesting. Right.
I can see the Photoshop.
She has an accent. If I go here. Wow, I can. Let's try somewhere else. Okay, that's English. Yeah. I was like, when I was listening to it, I couldn't tell, right? I mean, it must have been Māori, but otherwise I would have understood it. You know? Like, yeah. But yeah. Also visible. It's like, if we go here. No, not here. Not here. If I go, most popular song, that one. This. Yeah, there we go. How much Māori as recorded by the system. But yeah, so this is a pretty cool thing that we made. Unfortunately, it's like not public. But it's not public because the radio, like the language that's being spoken on the radio is considered basically, like, I don't know, to call it proprietary isn't quite the right word, you know, but the idea is that the Māori radio stations want ownership over that audio. Te Māngai Pāho pays them to do it, but they pay because of a treaty settlement process, you know. So they still have ownership over the stuff that gets produced. And yeah, all this purple here is music. So you can definitely see other patterns. So there's other patterns like, you know, after 7, just play a whole bunch of music, you know, don't bother paying people to stick around in the radio station because that's like dead time anyway. And then like in the peak hours, so 2 o'clock, 3 o'clock to 6, throw out as much English as you can because people are actually listening now. And then after that, go back to Māori. Yeah, obviously, the iwi radio stations, they're also trying to like build listenership. So they also want to be welcoming to new listeners, whether they speak Māori or not. And so that's, yeah, but this is kōkako. And I don't know what else I had to talk about after this. Right, so yeah, contact us, dragonfly.co.nz, it's our website. The fact that the domain is open is probably a big reason why we took that name in the first place. Yeah, I'm Caleb. If anyone has any questions, feel free to ask. But other than that, it's nice to talk to you all.
Yeah, let's open it up now.
Yeah.
I just wondered, that visualization was really cool. Do you use a particular software, or do you just build it from the ground up?
It's built in Ember.js. I'm pretty sure that nowadays, I'm like, is Ember still the new hotness? It's probably not, right? No. Yeah, it's not. yeah, and that's because it's like 3 years old already. Well, 2-ish, you know. So when it was made, I don't know if it was good then, but yeah. So there's definitely some, what's the word, as we like to say, I don't know, transfer costs or, you know, like associated with switching out from Ember, but also the design for kōkako won like some really big awards for, you know, graphic design, so which you can kind of see why. Yeah. Anything else? Yeah.
So you're not actually doing speech recognition, you're just doing pretty well speech recognition, but you're not actually parsing the words.
That's true, but interestingly enough, speech recognition is a separate project. Yeah, so we actually have done speech recognition, and like,
Of Māori.
yeah, of Māori, yeah, in Māori language. Where is that? So that's here. This project was I should tell you, was undertaken by Te Hiku Media, and so Te Hiku, they're the iwi radio station for Kaitaia. His Royal Highness is coming to Waitangi in a few days, and they're going to live stream it, so that's why they've got that big graphic there. Anyway, so Te Hiku, they're the iwi radio station for the far north. They're also quite keen technologists themselves. They built this website from scratch. They were also doing live streaming before it was a thing, using Raspberry Pis and AWS, which is like pretty impressive. But anyway, so they approached us to help work with them on the speech recognition project. So what's this? Like, what should I say? I shouldn't say my name because my name's not a Māori word, and so it will like fail. Kia ora e te iwi. Oh, kore te iwi. Ouch. Ka nui te pai tērā. Yeah. Ka whawhai tonu mātou, ake. Okay, not bad. Well, actually, that's bad. But it's oh, it doesn't matter. I won't dig myself deeper. I was practicing it just earlier today because we've got a new model that we trained and like we only just deployed it. Like, as is always the case, your model performance is definitely improved, but seeing it in the output is tricky because it's like a subjective thing, you know? Like you assign numbers to these things, but ultimately the real judge is like the person, you know, user experience is the real judge in the end. But yeah, anyway, I don't want to take up any more time. You're welcome to ask me about all of this afterwards, you know, but I hope everybody enjoys the talk. Yeah, so over to you. Thank you.
Yeah, thanks again. So
You're
you
welcome.
guys are hiring over at Dragonfly? Or?
We actually are soon.
Okay.
Yeah, the only reason I didn't bring it up is because we're going to have the conversation about it tomorrow. Yeah. But basically for the speech recognition work, we've got a whole bunch of funding from MB, which means that we can kind of grow our operation, get more excited people in working on the Māori language stuff. You saw the speech recognition demo, and it's one of 3 demos because we're also working on pronunciation modeling, so that if you like say the word but you say it with an accent, it can like kind of highlight to you where that's happening. And we've also built a voice as well. So we've got a voice. Auntie Evelyn from up north donated her voice, and so she gets to be the first voice of what we're calling Piki, who is like our voice assistant thing that we're working on.
Cool.
Anyway.
Yeah, so our keynote tonight,
Mhm.
yeah, thank you very much again, Joe. So I should have asked you, William, Caicedo. Yeah, and William is a senior data scientist at Media, and also does is at AUT doing research using CNNs to predict patient mortality inside intensive care units. So it sounds really interesting work. And and just saying, I meant to steal the document.
Oh yes.
Right, thank you. Cool. All right. So, pop that on your pocket when you get a moment.
My pocket?
Yeah. And hey, thank you so much for being here. Thank you.
Any pockets?
Just add a few way. Maybe the breast pocket here. Yeah. Will work well for the video. And we're going to try and balance your laptop here, or
I think it's okay.
yeah.
Put it here. Hello, everyone. It's nice to be here. Thanks to the meetup and Joe for the opportunity to share a little bit of my work or the things we're doing at AUT. So, as he said, my name is William Caicedo. I'm actually from Colombia, not from New Zealand, of course, and I came here to study a PhD, and things have been really interesting so far. I'm a software developer by trade, but since a little bit of time already, I decided to go into data science. So that's the reason why I ended up working with AI and specifically with in the medical domain, because I'm kind of a failed doctor. I mean, I wanted to be a doctor, but in the end, things went differently. But I ended up doing similar things. So yeah, we're going to talk about interpretable deep learning. In a minute, you're going to see why it's a big deal for the medicine field. So I hope you enjoy it, and here we go. So this is the outline.
Oh, yeah, sure. Yeah, cool, sweet. So,
Okay. This is the outline for today. Of course, who am I? And I explain why I ended up doing this. A little bit, we're going to talk a little bit about why deep learning is so popular nowadays. Everybody seems to be talking about it. Why this thing called interpretability is actually a need, what is needed. And then after we talk about that, we're going to see a couple of ways of extracting interesting stuff, interesting insights from trained neural networks. And I hope to be able to share with you some code, a little bit of code in a Jupyter notebook, so you can see how these things are actually done in Python. And of course, questions, feel free to ask at any moment. That's okay. All right, so what I'm doing right now, well, I'm doing two things. I'm a PhD candidate at AUT. I've been working on my doctorate for 2 years and a half now. I came to New Zealand in 2017. And my thesis is about, my research project is about predicting mortality in the ICU, the intensive care unit, using deep learning. The funny thing is when I talk about this, I always get this, like people saying, ooh, that's morbid. That's like, what now? Machines are going to decide who lives and who dies? And that's not the idea. It's quite the opposite. Because the thing is that doctors already have statistical models to try to predict who's going to live and who's not going to live. And they don't do this just to like condemn people or to kill them before the fact. They do it because it's a very good way of benchmarking the performance of ICUs. Because if you have a bunch of patients and you apply these prediction models and the models say the patients should live, if the patients die, something's wrong. And then they use this to debug what's happening in the ICU. And they benchmark their performance and they evaluate clinical practice. These scores are based on statistical techniques that come from the 40s, 50s, I don't know. But there's a reason for that. And the reason is that medicine is very resistant to change, and that makes sense. Because only what's being tested, but like battle tested, that's the things that get used. But these techniques, they make a lot of assumptions and their predictive power is limited. And then artificial intelligence is like, I mean, the predictive power of neural networks is, we're seeing it every day in the news and a lot of applications. But the issue is that they are not as interpretable. And we're going to see in a little bit what this interpretability thing means. So I'm working on that, trying to apply deep neural networks, specifically deep convolutional networks to this problem, using not images, but just patient data, like physiological measures and signs and all of these things. And at the same time, because I'm wrapping up the PhD thing, I'm also working as a data scientist in a company called Movio. This is a company that does analytics for the movies and cinemas. So the idea is that based on behavioral data, you can actually predict what movies is someone more propense to watch. And then the cinemas and the studios use this information to develop targeted marketing campaigns. For example, we're able to identify who is more propense to watch the next, I don't know, Avengers movie, for just one example. And then given this, we can target the group of likelies or the group of unlikelies. It depends on what kind of campaign you want to build. And we do this using different means. But then at the core of everything is machine learning. So it's a pretty... I never, before coming into the company, I never thought that that could be even a thing, right? Like machine learning, the amazing idea of like chucking a really big count net into 2 GPUs, and it works so good that the next year every leading team was using a deep convolutional network. But before that, it was just like, well, neural networks, it doesn't work. But it actually works. It took a while, but it really works. And models like the ResNets, the SSD, YOLO, all of those models are actually the state of the art in all of these applications. Not only that, but if you talk about natural language processing or natural language understanding and machine translation, the kind of thing Google Translator does, it's also deep learning. Specifically, a type of network called a transformer. And like every day, there's something going on in the news. Someone came up with an even bigger network, even bigger transformer, and then the machine translation thing is really amazing to see the kind of things they are able to do. A company like, the big companies have so much data and access to pretty big infrastructure. So they are able to do really, really interesting things with this. Speech synthesis, the WaveNet. You've heard it. You've heard how voices actually sound like the real thing now, as opposed as a decade ago, in which you were really, really aware that you were talking to something that didn't sound human. But nowadays, the gap between the human voice and the synthesized voice is getting narrower and narrower. And a big impulse behind this is actually neural networks. The WaveNet is a convolutional neural network trained on audio. And this is really huge and really interesting. Not only that, but we have new exciting applications. We're able to synthesize images, synthesize sound out of nothing using a specific type of network called a generative adversarial network. I don't know if you've seen, there's a website called This Person Doesn't Exist. Maybe some of you have seen it. These people, they don't exist, and they look, not all of them, of course, but a lot of them look really convincing. So I wonder that maybe in 10 years, if you want to launch a new product and you need a model, probably you won't hire a human. You just synthesize some face. And yeah, that's actually the future. And this is also neural networks. And this is what I've been working on, medical diagnosis using EMRs. A while ago, someone had the great idea of taking medical charts and putting them into computer systems. So now we have a lot of data. That data is searchable. Even the free text data that the doctors write is also, we can use that and we can improve diagnosis with that. So it's a matter of time until we see that doctors are heavily augmented, not replaced, but augmented with AI. That's going to become something normal, something usual to see in doctor practices. Very good. And the sky's the limit, actually. We're just discovering the things that we can do with this technology. And this is really cool. Some people say deep learning is just experiments and trial and error. And that's kind of true. Sometimes this has much of an art, right? But theory is slowly catching up. We now are beginning to understand why deep neural networks work as well as they do. We are starting to understand why they didn't work so well in the past. The math is getting there. So when the math finally catches up, then probably new applications are going to come out, and we're going to be able to do even more exciting stuff. Okay, so in these domains like image recognition and object detection, speech synthesis, recognition, all these things, there's almost no choice but deep learning when you are talking about deploying something to the real world. But this technology is not perfect. There's no perfect technology. It has shortcomings, and yeah, we need to do something about that. The first shortcoming is that we call it artificial intelligence, but it's not actually artificial intelligence. Someone said once that it was artificial intuition. And I heard it, I saw that for the first time, and I said, it makes a lot of sense. Because the kind of things you're able to automate are the things that take 2 seconds for a human. It's a dog, it's a cat, it's this, I mean, perceptual tasks. When you have to really think about it, when you have to come up with a plan, when you have to weigh different possibilities and establish a path, that's another business. That is another business. There are other techniques for that, but then deep learning probably has to be augmented. When we take a look at the kind of technology that autonomous cars use, you see that deep learning is just one little part of the whole technology stack. And the thing is that it's artificial intuition, which means deep learning doesn't care for causality. If your data sets show a correlation between a label and a feature, a neural network is going to look into that and it's going to try to find a relationship between those two things. It doesn't matter if there's no causality relation between them. And that's very important. We're going to see a couple of examples in which this thing happens, and we're going to see how you got to take care that that's not actually something else. And for the same reason, deep learning models can fit noise really, really easy. So if your data set is really noisy, if you have weird stuff going on, maybe your network is going to be weird at the end. And it's like the classic saying, garbage in, garbage out. You gotta be really careful with this. Because of this, you see deep learning in certain domains is tricky. It's even dangerous, and you gotta take care of doing the right thing. Here we have one example, because, well, medicine is, you can see how medicine is something that you should be careful about. Someone I really respect said that radiologists were like on the way out. At the moment I said, yeah, that's true. But then some years have passed and not so much. We're still not there. Because ComNets are really good at object detection, image classification. So someone said, yeah, the most natural thing is using deep learning to automate the tasks of the radiologists. If someone has, for example, here an X-ray of a chest, then if you're looking for something that's not right, maybe you have a deep learning model or an artificial intelligence model doing that for you, and then instead of having 10 doctors, you could have just one doctor, and this doctor wouldn't have to review every single X-ray, because the machines can do it automatically or autonomously. And, well, we are not there yet. And this example is going to show you why. So in this particular task, someone trained a deep network to detect something called cardiomegaly, which means an enlarged heart. So if your heart is enlarged, I mean, that's not good news. That is not good news. So if that's going on, then your doctor has to be aware of it. They have you take some X-rays, and then they decide what to do. So this person here has an enlarged heart. I only know because I read the paper, but I don't really understand an X-ray. I have no idea what's going on there. But I do know this person is sick. So someone trained this model, right? And in the test set, this model does really well. So for this particular case, it predicts there's a 75.2% chance that this person has cardiomegaly, and that's the case. So it's actually predicting the right thing. This person is sick. Okay. Well, I would have said, yeah, let's go. Let's put this into production. We're going to save lives. We're going to revolutionize the medicine. But that's not the case. We're going to see why. What you see here is a technique to try to make sense what the neural network is seeing I'm not going to go into details right now because in a moment we're going to see a little bit more about it. But for now, we can see, I can tell you is that every little square has a number, and that number is related to how important is this little square for the prediction. So remember that the network is predicting that this person is sick. So those numbers over there tell you how important is each square. For example, something like this is not really important because it has an importance of 0.22, but something like this is really, really important. This is a heat map. Heat map, yeah. So you can see that it kind of makes sense because the heart is here. So if you're actually trying to figure out if this patient has an enlarged heart, then the attention of the network should be in this area here. It doesn't make sense that this over here is really important because that's not close to the heart, right? So we would say, yeah, it's making a good job. It's probably detecting cardiomegaly, and the prediction comes because of the right reasons. Something's going on in the heart area. But if you take a hard look into it, you're going to see that the corners are very important. This corner, not so much. That's just 0.25. But this corner over here has a really high importance, and it shouldn't. As well, this one as well. This one over here and this one over here. And that's odd. Why the corner should be important to predict an enlarged heart? I mean, we kind of know that a human doctor wouldn't look at the corners of the image. A human doctor would concentrate on this area, right? Okay, that's odd. That is really odd. Another patient. This person also has cardiomegaly. The network, once again, predicts the right thing. We're really happy. But then, look at this. These corners are also important. Now, the numbers are negative, which means those areas are important not to predict an enlarged heart, but to predict the opposite. This person does not have an enlarged heart. So it's even more interesting. Why those areas over there are related to the wrong thing and with a really big magnitude.
So is it 1.4 or 14?
1.4. 1.4. And the one next to it is 2.4. And yeah, what's going on there? That's really interesting. Why that corner would suggest this person is not sick. All right. So what's happening here is that those two images came from two different X-ray machines. One came from a portable X-ray machine, and the other one came from a regular X-ray machine. And you would say, you would ask, what's the difference? If you're really sick, they can move you into the X-ray machine. They bring the X-ray machine to your bedside, and they take the picture right there. So it makes sense then that the people that are more sick, right, have a bigger probability of having X-rays taken with a portable machine. Since these models are really powerful, they're just looking for something to, like, any correlation to latch on, anything that can be used to predict what you're trying to, for it to predict. The model found that this little thing, it's like a BH, some characters here, are correlated with the probability of sickness, right? So what would happen if we just feed images coming from a regular X-ray machine to this model? Our predictions would be biased and skewed, and then the performance in our test set wouldn't be representative of what would happen in real life. We would never have detected that this was the case if we didn't have this tool. So you can see that the right prediction is not the only thing that matters certain times on certain tasks. You also have to predict the right thing for the right reasons. Very well. Another example, still on medicine, which is not the only sensitive domain that there is, but it's a really interesting one. In the 90s, not yet deep learning, just regular two-layered neural networks and all sorts of regular algorithms. There was this one study. They were trying to predict they were trying to classify between high-risk pneumonia patients and low-risk pneumonia patients. It's an interesting tool to have in triage to better use resources in an ER. So if you have someone with a high risk, with pneumonia and a high risk of complications, you would treat that person first. So someone said, let's use artificial intelligence, machine learning to try to solve this. And they tried different algorithms. And show consistently a lower risk of complications. So if you have a pneumonia all of a sudden, you're going to rush into the ER. If you have a cardiac disease and you've developed pneumonia, you're going to rush into the ER. And not only that, you're going to have checkups that are going to be more regular than someone that doesn't have any of those things, right? So in the end, the thing was that these patients, the asthma patients, were being treated much more aggressively, which meant in the end that their survival rates and the rates of complications for these patients were lower. So it's completely the opposite thing when you think about it. The model, instead of saying, you know what, this person has a high risks, so let's admit them first, he was saying the opposite thing, but the model was right. The data we were supplying to the model was wrong, or at least it was improperly curated, so it was showing the wrong correlations to the model. For the doctor, it's really easy to spot this because they have the causal knowledge, because they study this. But the machines, at least deep learning or neural networks, they know nothing about causality. They only know about correlations. And that's why this kind of thing happened. In the end, they tested it was a tree neural network. I think the other one was a rule-based program. And even though the neural network was able to overperform the other algorithms, they decided against the neural network. Why? Because in the rule-based program, you could just eliminate the rule. This rule doesn't make sense, let's take it out. But how do you do that with a neural network? You have to retrain it. And not only that, you have to really, you have to take care of presenting it a really well-curated data set. So it didn't matter that the neural network had a better performance. What mattered in this case was that the rule-based model was interpretable, which means humans could make some sense about the reasons behind the prediction. So I've been saying interpretability over and over, and you wonder what's a rigorous definition of that. The thing is that there is not. There are a lot of definitions floating out there, but whatever it is, in rigorous terms, it involves being able to explain how input features affect outputs. It's about giving not only a prediction, but a justification, but a mean of making sense where this prediction come from in terms of the inputs we are supplying to a machine learning algorithm. And yeah, you probably have heard a lot of times things like neural networks are black boxes. Neural networks cannot be used, cannot be trusted because we don't know what they do. And that's not true. That's really not true. And traditionally, there are other algorithms that we may think as interpretable. Like, for example, a decision tree, because you know exactly, supposedly, you know exactly what's the path you run down the tree to go to a certain prediction. But if you have a really gigantic tree, which can be the case, good luck interpreting that. Or if you have not a tree but an ensemble of trees, good luck having a clean, neat interpretation. So we can see that not only neural networks give us a bit of trouble to interpret, but in the end, other algorithms that are supposed to be more interpretable than that. That means that we can actually make sense how this specific input affects the output. They also can give you problems when you're trying to interpret them. Than we might think. A lot of research has been going on in this area for at least the last 5 years or so, because this has been recognized as a problem. And in my experience, when you go to doctors and you say, you know what, doctor, I have this algorithm, it's much better than the statistical model you're using to predict this or that. And they say, that's amazing, let's use it. But when you show the data or the predictions and it's performing really good, they say, that's amazing, but tell me why. Why? What this algorithm saw in this patient, so it predicted this patient had this or that, or was he or she were going to die or whatever. And then as a machine learning engineer or data scientist, let me think about it. And not only because they don't trust the machine, it's also because they want to learn. I've had this specific situation happening to me quite a few times. They want to learn. They want to find new knowledge about their practice. So it's really important to have these tools to not only offer a prediction, but something else. There's something called LIME, which is a model that's based on local approximations. We're going to talk a little bit more about it in a minute. There's something called mimic learning. There's something called input occlusion. That's exactly what they did with these X-ray images. And there's something really interesting called the shapely value. It's just 4 techniques that can be used to interpret deep neural networks. Not only deep neural networks, you actually can use some of these to interpret any black box. It could be, for example, a gradient-boosted machine, which are really popular right now because they offer a really nice performance for a lot of problems. But they are not as interpretable as a single tree. So you can possibly use some of these to get explanations out of those models as well. So LIME is a tool that was introduced in a paper by Ribeiro et al. In 2016. So it's not very old, as you can see. It's last 3-4 years. I like this phrase, everything's linear if you zoom on it close enough. If you have a really complicated curve in a plane and you zoom on it in a really small range, it's going to be linear. It's going to be like a straight line. So essentially what they do is that if you have a really complex algorithm, in this case a neural network, and you want to understand how it works or how the inputs are affecting the output, you approximate it with a linear algorithm. It could be a logistic regression model in a very specific subset of the domain, small enough as so the linear approximation really agrees with the predictions of the neural network. And if you do that correctly, you can actually use this linear model as a substitute of the big model. And since a linear model is well specified and you have some input variables and each input variable is associated with one coefficient, you can actually take the coefficient as the importance of the feature. And in this example, that's what they did. They approximated the performance of neural network that was trained on ImageNet to do image classification using this LIME thing. And as you can see here, they can show you what pixels, what parts of the input are most correlated with this specific labels. For example, that's the original image. This is the bit of the image that's the most correlated with the label electric guitar. This explains acoustic guitar, and this explains Labrador, a dog. You can see that it kind of makes sense. So if you were the engineer behind this, and these are the results you're getting from your debug stage, you'd be confident that the network is actually attending to the right thing. So it's predicting the right thing because of the right reasons. All right? Mimic learning. This is another way of using a surrogate model to interpret a much more complicated one. So in this case, you have a neural network right here. Let's call it a black box. You're trying to predict what's going on this input, classify this. This is probably a dog, right? So you train this on this data. It's really good. It predicts that the dog, it's a dog, 0.7 probability, right? So it's giving you good results, but you cannot interpret it directly. So what you do is that you get another model that's interpretable, and you train it on the same data set. But instead of using the original labels, you use the predicted labels. So same inputs, different outputs. And it turns out that when you do this, it's much more easy. It's much easier for the interpretable model, for the surrogate model, to solve the original problem, compared to if you were just using this from the beginning, trying to predict these labels using these inputs. The performance is not going to be the same, but it's going to be close enough. And if you are working in a really complicated domain in which interpretability is really important, you are probably willing to trade a little bit of performance for interpretability. So this is what these guys in 2016 proposed. All right? Sensitivity analysis or occlusion analysis. This is conceptually probably the easiest of them. So if you have that image and you want to know why the network is predicting what it's predicting, what you do is that you systematically occlude parts of the image. You replace that for something. In this case, a gray patch, right? And you do this with every possible area of the image, and you, at the same time you're doing that, you record what happens to the predicted probability. And then you can build a heat map, and then you can superimpose it into on the original image, on top of the original image, and you can know what parts of the image are most correlated with the predicted output. That's what they did with the X-ray image. This is conceptually easy. You don't really need really complicated machinery to pull this off. And if you're already working with neural networks, it's really easy to do this and offer something else, not only the prediction, but something else. We can see here that, this is really funny. It's predicting Pomeranian, which is a dog, but then the weird thing is that the areas, if I'm reading this correctly, it's probably, I'm not. But the most interesting parts of the image are not as important according to this heat map. And that's really interesting. Maybe I'm reading it the wrong way, but in any case, it's a cool tool to have. All right. So what are the shortcomings for these models we've seen? The first one is that you're not using the real thing. You're using a fake in both Lime and mimic learning. In Lime, you're using a linear model to approximate locally your neural network. In mimic learning, you just say no more neural network. You just use another model, and you trade off a little bit of performance for that interpretability. Sometimes that's not a good thing. Because, sometimes you need as much performance as you can. That trade-off is not so easy to make sometimes. And in the case of occlusion, something happens. If you occlude one part of the image at the time, you might be missing interaction terms. That means maybe something that's occurring here is really correlated to something that's occurring here. So the right way of understanding the importance of these two regions is considering them not separated, but as one thing. The problem is that if you try to do that, you end up with a combinatorial explosion of possibilities to occlude. So that's really difficult. But it can be a problem. There is another alternative that's called the Shapley value. And this is something I'm using in my PhD thesis. The PhD value is, it's a really complicated formula, but that's not the point. The thing is that many years ago, Lloyd Shapley came up with this formula, and there's a bunch of proofs that say that this is actually the most.
Does this do anything with that kind of continuous variation, or is it just more of a Boolean thing?
So this algorithm, it actually doesn't do the variation. What it does is that it has a set of rules that they take the prediction and decompose it without you having to change manually, or the algorithm doesn't have to change the values of the inputs to do that. So you don't have that problem. Actually, that was one of my misconceptions at first when I saw this algorithm, because I thought, okay, so this is calculating a Shapley value, so I should probably, since these are not discrete inputs, what if I try different perturbations of the input? But then, upon further inspection, I found that what it does is it takes the predicted output and back propagates it through the network and distributes it on the inputs without having to vary the values of the inputs.
Okay, and the information you get out of that back propagation, is that representative of is it sort of deep enough information to give you what you would get if you did all the variation, or is it more equivalent to what you just did the Boolean?
I'm going to show you what you actually can get out of it.
Just a heads up, we need to be all out of here in 10 minutes.
Ooh.
So maybe 5 minutes, like that time we'll wrap up.
All right. All right, so this is the kind of thing you get out of it.
Sorry, that's not exactly the advice I would have given you.
It's okay. So for example, this is a patient for which we have recorded several variables during 48 hours. And then what you see behind the data points is the expected value of the importance of each data point for the prediction. So the things in red actually are evidence for death. And the things in blue are actually evidence for survival. This is the expected importance of this data point, for example, if it was present on the input, and not only that, if it was present, and also considering if it was present and all the other things were absent. So all possible combinations are taken into account here. But this is an approximation because computing the real thing wouldn't have been tractable for us. So the cool thing about this is that you can see, for example, these variables over here correspond to something called the Glasgow Coma Scale. It's a way of assessing your mental state. So, for example, this is really bad. This is normal over here. So you can see that the network actually starts to give more importance to the wrong values of the input. That makes sense. If we find something that doesn't make sense, it would be like a big alarm for us. Something is not going the way it's supposed to be. There's another library called SHAP, which does the same thing by a different method, but not only for neural networks, but for every algorithm you can think of. And not only that, it's a general framework, mathematical framework that unifies everything else we have seen until now. It can potentially explain any machine learning model using an approximation to the Shapley value. And this is the kind of thing you can do. You can actually superimpose the importances on the real inputs and provide this kind of visual explanation, which actually is pretty cool, to the end user. all of these things, both DeepLift and SHAP, are available as Python packages you can also install. So we have seen that there are ways of interpreting neural networks and machine learning algorithms, so you don't have to sacrifice your model to appease the interpretability gods. That's a good thing. That's the reason why we are able to use deep networks for our research in ICUs. All right, thank you very much. This is, you can take a picture of that. That's a link for a Jupyter notebook that shows how to use the SHAP library on a Inception neural network pre-trained on ImageNet. It's a really cool library. It's really easy to use, and if you have the opportunity, go ahead. So thank you very much for your time. Thanks. Thanks. Thank you.
Thank you, that's right for him. Should we take maybe like one question from the floor before we all run out the door? There's one person.
Mine's just a cheat question. Will this notebook be uploaded to like the meetup page?
Yeah, are you
Sure, I can.
slides?
Yeah, I can give you the slides, so that's gonna be there, and the notebook is on Colab, so it's gonna be there pretty much forever.
Awesome. Yeah. Okay, cool. Maybe we'll make our way around down the lift. But then, is it raining out there, or anyway? There's a sheltered area down the bottom in the lobby and outside. Nice sort of patio area where maybe you'd be willing to hang out.
Yeah, sure, no problem.
We can chat and do some more Q&A there. So once again, thank you all so much for coming. Thank you.